Yeah. Okay. So traffic types were traffic marking, signs, and signals. This is the manual we follow. This is what manual covers. These are the requirements of a good traffic control device. Important principle in communicating or designing a traffic control device is redundancy, takrar. Okay. Some examples for redundancy in different types of traffic control devices. Then we discuss traffic markings, they are of three types. Then we discuss traffic signs, they are of three types again. And then we discuss traffic signals, which are of 9 types. Then we discussed some guidelines and benefits of having traffic signals. Some indications, traffic lights, different types of traffic lights. And these are basically sight distance requirements for traffic signals, and they depend upon 85th percentile speed. Okay, so you can see the speed increases, we need more sight distance because it will take more time for us to stop if our speed is higher. The difference between this one, this sight distance, and any other type of sight distance is the position of the signal. So you know the signal could be on the side of the road, it could be on top of the road, but normally it is more prominent, okay, because it is at a greater height than a normal car or a truck even, okay, because we want the driver to see it from afar. So side distance requirements are normally much easier to meet with the signals, but this is something which we need to check, okay. So when we are designing intersections and we are going to decide that we are going to put a signal on this intersection, we need to check the sight distance for the signal itself. Okay, now some terminologies which we need to understand before we move on to analysis of the signal. The first one is signal cycle. So signal starts, usually start of signal is considered the start of red, any red. After red it goes to yellow, then green, then yellow, and then it becomes red again. So when the from the start of the first red to the start of the next red, this is considered as the complete cycle of the signal. Okay, from start of one red to the start of the next red. So when your signal was red, other directions were having green, right? So when your signal became yellow, all other directions became red. Okay, so when you go from one red to the other red, all directions complete their time. So your time was completed during yellow, green, and so on, and the other directions time were completed when you were having red. Okay, then we have the cycle length, which is the time taken by the signal to complete the cycle. We have discussed it earlier when we were discussing counting at intersections and delay studies at the intersection. We discussed cycle length and cycle. Then we have the interval. Interval is the time of one signal indication, one signal light. Okay, so during one interval, signal light remains the same, it doesn't change. Then there can be different types of intervals. We have change interval, which is another name for yellow. Change interval is another name for yellow. I may have mentioned in the last lecture as well that in Bahrain we have two types of yellow, from green to red and then from red to green. Okay, this what they are talking about in the book is the one going from green to red. Okay, because that one is more critical, more dangerous. People are moving, so they need to decide when to stop. Okay, so this is more critical. So another name for yellow is change interval. Then we have clearance interval. Another name for clearance is all red interval. So as the name suggests, all signals are red. Okay, all signals are red, and this is given for clearance. What do we mean? You pass the intersection during yellow time. Okay, you didn't have a stopwatch, you didn't know for how many seconds the signal will remain yellow, you didn't know how many seconds you will take after crossing the stop line to reach the other side. So in most of the cases, when you cross during yellow, before you reach the other side, before you clear the intersection, the signal behind you will become red. So if the next one immediately becomes green, it is risky for you and the other driver. Okay, he may look at the green and enter while you are already there. Okay, so we give some gap between the red of the first phase and the green of the next phase. Okay, so this gap is called as all red. Okay, so your signal is red and the next one is still not green, so it's all red. So another name for all red is clearance interval. Then we have the green interval, we have the red interval, you already know about that. And then we have the concept of phase. Phase is the total time for a movement. Okay, the total time available for a movement. So it includes three intervals: green, yellow, all red. Green, yellow, and all red. So when we say this is phase number 1 and this is for the eastbound direction, that means in this phase the eastbound direction will start with green, then it will go to yellow, and then it will have all red. When the all red finishes, the phase of eastbound finishes. Then we have how signals are operated. Signals can be operated in pre-timed manner, they can be operated in semi-actuated manner or fully actuated manner. Pre-timed means signal is not attached to any sensor. Okay, the signal timings are fixed by programming before the signal is installed. Okay, so you have to, as the programmer of the signal, you have to know in which signal timing should be programmed. Okay, because signal will not consider any change in traffic conditions by itself. Okay, so you need to know which one is a peak hour, which side will take more time in the peak hour, will need more time in the peak hour, which one is an off peak hour, and what should be timing in that. So everything is fixed by programming. Okay, and it has no connection with the real traffic. Okay, the real time traffic. Then we have semi-actuated and semi-actuated. Now you have an intersection. Intersection means what? Two highways are crossing each other. Okay, two highways or streets or whatever, two roads are crossing each other. So in semi-actuated operation, one of the roads has sensor. One of the roads has sensor. Okay, and semi-actuated is applied where you have a major road and a minor road. So semi-actuated operation is applied where a major road is crossing with a minor road. Okay, now if I want to put a signal on one of these roads, a major and minor, okay, which road will have that sensor? Major, minor. So if I am going to use a semi-actuated signal and I want to put a sensor on one of these roads, so which road will have this sensor? The major road or the minor road? Tell me. Okay. Yes, what about these other 5 people? It counts 6 including me. So what about the other 5 people? What do they think? Major road will have the sensor? What about the other 4 people? You guys can see my screen, right? So you know what I'm doing, right? You know what option I'm going to select. See, this one. Okay. So we are the only 2 people correct here, huh? Somebody saw me and he or she, no, she, definitely she. All of you are she, right? So he went with my option. Okay, so this is the correct one. The minor road will have the sensor. The minor road will have the sensor. In semi-actuated operation, minor road has the sensor. What's the logic behind it? On the major road, I want continuous flow unless somebody comes on the minor road. Okay, so there's a major road and there's a minor road. Major road traffic will have default priority. will have default green. Okay, and this default will only change if the sensor on the minor road detects a vehicle. Okay, once a vehicle is detected on the minor road, the signal will become green for the will give green time to the minor road for its minimum duration. Okay, if during that duration another car comes on the minor road, it will extend the green by some interval. So we are fixing these values. Okay, we have to fix that. If a car comes, if you detect one car on the minor road, be green for 4 seconds, for example. Okay, if another car comes, give it an extra 2 seconds, then an extra 2 seconds, then extra 2 seconds. If cars keep on coming on the minor road, the green will keep on extending by a fixed interval. Then you put a maximum green as well. So you can keep on adding 2 and 2 and 2 for every extra car from the minor road until you reach 15 seconds. After 15 seconds, the major road has to have the green again. Okay, and the next green cannot be before 30 seconds. Okay, so we fix these ranges. Okay, so we fix how much should be the first green interval, we fix how much should be extension in the green interval, we fix how much should be the maximum green interval for the minor road. Okay, and it only activates all these things only activate if there is a car on the minor road. If there is no car, then the sensor will not detect anything and the major road will have green. So for example, there's off-peak hour, okay, and there's nobody on the minor road. So if there's nobody on the minor road for half an hour, that half an hour for the major road will remain open. Okay, so this is why we have the sensor on the minor road. Okay, then we have fully actuated signals. Fully actuated signals are used where you have two major roads crossing each other. So we have sensors on all directions, and these sensors obviously then are changing the timing of the signal for all directions on the basis of traffic. Okay, and so going back here, so sensor is changing the interval duration, right? Interval duration changes, phase changes. When phase changes, cycle changes. Okay, so in a fully actuated signals, all these things can change. Okay, fully actuated signals may change the order of the sequence of the movements as well. So if you have most probably, obviously, you have some signals on which you pass through on daily basis. Okay, so when you are passing through these signals, you know that after which side your turn is going to come. Okay, so I know I'm always after the side which is the opposite to me, I get the turn after that. Okay, so when they get the green, I'm ready now because I know this is my the next turn will be mine. Okay, so this is the order which is fixed, but in fully actuated signals this order can also change. Okay, so normally it is east and then west, but when the east was going on, the north side has too much traffic, so from east it goes to north as well. It can happen. Okay, or there's nobody on the west side, so the west side can be skipped as well. Okay, this can also happen. So this all these the point is everything can change in fully actuated signal, but within the range. So there is a maximum minimum range for the green time as well as for the cycle time. So yes, everything can change, but within the limits. So whenever we have actuated signals, we are allowing the signal some flexibility, but we are giving a particular range as well. Then we have signal coordination, okay, which is applied where a main highway has intersections close to each other. Okay, when a main highway has a series of intersections close to each other. What do we consider as close intersections? One which has a spacing of less than 0.5 miles. Okay, less than 0.5 mile means around 800 meters. Okay, so when intersections are in sequence, they are on a main highway and their spacing is less than 800 meters or 0.5 miles, we can coordinate these signals. Coordination means what? When we are designing them, when they are planned for timing, when the timing are being fixed, we fix the order as well. So from after the first signal, the second will become green, then the third will become green. So they will become green in order. Okay, and you should understand the logic behind it. When the car passes from the first signal, it will go to the next one. So the next one should become green. Then it will go to the next one, then the next one should become green. So they will keep on becoming green in sequence. Now the issue or the main design consideration here is the interval between the green of the first signal and the next one. Okay, this interval is called as the offset. Okay, so what is an offset? In a coordinated series of signals, an offset is the time interval between first green and the second green, or the second green and the third green. Okay, so between each two signals there should be a time interval, and this is a time interval the car is taking to go from one signal to the next. Okay, the time interval the car is taking from one signal to the next, and obviously this time comes from distance, right? So from first signal to the next one I have 500 meters. My speed is 40 kilometers per hour. So I can calculate how much time the car will need. There are some highways which have these coordinated signals in Bahrain, and there are many highways which should be coordinated but they are not. And the main problem is that we need two-way coordination there. So there's a series of intersections near Al-Anbar and Tubli. There is the series of intersection near the old campus in Isa Town. When you are coming out of the education area and going under the bridge, there are 2-3 signals there. Okay, and there are other series of signals which become jam-packed, like in the morning hours when the schools were happening and so on. The coordination should be done. Okay, but in some cases we face a problem that traffic in both directions is very high. Okay, or traffic in different roads is very high. Coordination, you can see if I am green, if I am giving green to one direction, okay, to go from one signal to the next one to the next one, to this direction is having priority, right? What about the other direction? What about the other road? They have to wait, obviously. So this coordination works best when you have a particular direction which has very high traffic, and you can give preference to that direction without harming the other directions. Okay, without creating too much queue on the other direction or the other road. Okay, so coordinated signal means you are giving priority up to a particular highway and to a particular direction. Okay, so it only works there. If you have two-way or two highways which are very having high volume, then the coordination is not practical there. Another problem is you are doing coordination, but your direction has so much volume that even with coordination you are having long queues. Every highway, every signal has a capacity. So if your demand goes above capacity, whether you apply coordination or whatever, whether you just remove the signal and make a bridge there, it will not work. Okay, so when the queue becomes very long, your offset doesn't work. Okay, your offset is what, how much time the car will take to go from signal 1 to signal 2. The car is stuck in a queue. It is moving like a snail. Okay, so it will obviously take more time. Okay, so your coordination again fails there. Like your coordination doesn't fail, but it is no longer effective in that case. Okay, so these are some scenarios in which coordination doesn't work. But if you have series of intersections close together, one direction has high volume and you want to facilitate that direction with signal coordination, you can achieve a non-stop flow for that direction, or a flow which is having less number of stops. Okay, a couple of other concepts. The first concept of saturation headway, and then we have saturation flow rate as well. Okay, first of all, what is the meaning of headway? We have talked about headway in chapter 1. What is the meaning of headway? Yes, anyone? What we mean by headway? Yeah, the gap between two vehicles, two cars. Okay. So saturation headway means what? Minimum gap between two vehicles. Okay. Saturation headway means minimum gap between two vehicles when they are crossing the signal. Okay. So you are standing at a signal and you are looking at the headway between the vehicles. Okay. When you reach the minimum value of that headway, this is called as a saturation headway. Okay. Headway is uh, headway is the inverse of flow rate. Again, something which we discussed in the first chapter. Okay, so headway is the inverse of flow rate. So when you take the inverse of minimum headway, it becomes saturation flow rate. Minimum headway is saturation headway, right? So when you take the inverse of saturation headway, you get saturation flow rate. Okay, so the general relationship is inverse of headway gives me flow rate. Inverse of saturation headway gives me saturation flow rate. If flow rate is minimum, if headway is minimum, then the flow rate is maximum. If headway is minimum, the flow rate is maximum because they are inverse, right? Okay. And then you can see here 3600. What is this 3600? Is the conversion factor. So the headway will be in seconds, obviously. It's minimum means it's a very, 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 very low value, right? In time. So seconds. And then the flow rate has to be in per hour, right? So that's why you see 3600 here. Okay. The basic relationship is flow rate is inverse of headway. Okay. So saturation headway is inverse of saturation flow rate. Okay. And because they have different units, so I need 3600 here to convert it to per hour. Okay, so if you are looking for saturation headway, I told you, you go at the signal, you note down the headway between the vehicles. When you get the minimum value, you reach saturation headway. Now this minimum value is normally attained after the fourth vehicle of the queue. In some cases after the third vehicle, in many cases after the fourth vehicle. The first 2-3 vehicles are normally slower, they take more time, okay, and they have more gap between them in terms of time, okay, not in terms of space, in terms of time. Headway is time, right? So the first 3-4 vehicles, they see the signal becoming green, they put their phone away, they change the gear or whatever, but the guys behind them, they get more preparation time. So that's why when they reach the intersection, they are faster and their time gap is less. So you get to saturation headway from the fourth vehicle or third vehicle onwards. This is how it happens. First 2 vehicles, more headway, then less headway, then less, and then at a point you will get to a minimum value. Okay, so this is your saturation headway. So when you start noting down the headways between the 2 vehicles, when the signal becomes green, this is the pattern you will see. Okay, this is the pattern you will see. It will go from highest to lowest. The first 2 vehicles have the highest, and from fourth vehicle onwards it becomes the lowest. Okay, if I take the difference between the lowest and the vehicles which were having more than the lowest, okay, so the lowest is fourth vehicle onwards. So if I compare this value of headway from the fourth vehicle onwards to the vehicles which were before that, the first 2 vehicles, the first second and third vehicle, third and fourth vehicle, if I take the difference between them, this is called as a startup loss time. Okay, extra headway basically, the extra gap which the initial vehicles have took in the queue. So this is called as a startup loss time. Okay, so every time the signal becomes green, you take it takes few vehicles to get to the minimum headway. So whatever you are getting more than the minimum headway is part of your startup loss time. So for example, your minimum headway, saturation headway was 2.5 seconds. Okay, the first two vehicles took 4 seconds. Okay, so 2.5 and 4, you got 1.5 seconds extra, right? So this 1.5 seconds is part of startup loss time. Then the next two vehicles, their headway was 3.2 seconds. So minimum is 2.5 and you have 3.2. So 0.7 seconds extra. So 1.5 from the first two cars, 0.7 from the next two cars. Okay, so this total will be your startup loss time. Okay, and then from other next vehicle onwards, you start seeing 2.5 seconds. Okay, so you achieve minimum. So whatever extra value you observed before it is all part of startup loss time. Okay, and we represent it with L1. In one phase of the signal, remember I told you one phase means green, yellow or red. Signal becomes green, you have startup loss time. Then at the end, we have something which we call as clearance loss time. Okay, clearance loss time. So clearance loss time is that time where the vehicles are approaching the intersection, but the signal has become yellow already. So they can see the signal yellow and now they think that we cannot cross. So they start stopping. Okay, so the time when they think that they cannot cross and they are prepared to stop, from this time onwards you have the startup loss time until the next green, until the next side becomes green. Okay, so we were on the eastbound side, signal became yellow and you thought, okay, I'm too far, I will stop now. So you stopped. Okay, so clearance loss time started. Now you stopped, signal maybe have 0.5 seconds of yellow left, then we have the all red time and then the next signal will become green. Okay, so this half a second of yellow and the all red time is part of clearance loss time. Okay, and we represent it with L2. Okay, so in one phase we have two loss times. Startup loss time when the signal becomes green and clearance loss time when the signal is at the end of yellow. Okay, so you add them both, you get the total loss time of one phase. Okay, did you understand this explanation? Any questions here? Okay, startup loss time, clearance loss time, clear? Okay, now if you take the total phase time of the signal of any movement, so you will take what? Green, yellow or red, you will add them together. This will be the phase time of one movement. Now from this phase time you subtract the loss time, and I told you loss times are two, startup and clearance. You subtract these two loss times, you will get a time which is called as effective green time. Okay, so we have a phase time, green plus yellow plus all red phase. Subtract L1 and L2. L1 is startup loss time, L2 is clearance loss time. You subtract them both, you get effective green time. Okay, now if you remember, after startup loss time, vehicles are moving at saturation headway. Startup loss time was before saturation, right? Before the minimum. So in effective green time, the headway between the vehicles is equal to saturation headway, the minimum. Okay, so if for example G is 10 seconds. So during these 10 seconds, vehicles have a gap of equal to saturation headway between them. In these 10 seconds, whatever vehicles are passing, their gap is equal to saturation headway. Okay, so this is the definition of effective green. And how do we calculate it? You add the phase time and subtract the loss time. This is how we calculate it. Let us look at one example to clarify the concept. Okay, this is a very rough example, very crude example. The calculation is very simple, but it will make the concepts clear. So we have a signal. The signal has cycle length of 60 seconds. So it takes 60 seconds to complete all the movements, complete all the phases. For one of the movements, the green time. Okay, so there are two green times. One is called effective green. this one, and the other one is the time of the green light, which you will add for the phase. Okay, so this one is the capital green, okay, which is when the time the time when the signal is showing green light. Okay, so this is not effective green. Then we have the yellow plus all red time, okay, which is 4 seconds. Saturation headway is 2.4 seconds per vehicle minimum. Okay, the vehicles reach a minimum headway of 2.4 seconds. Then we have the two loss times. Okay, now they want the capacity of this movement. Okay, so in 1 hour, how many vehicles can pass from this direction of the signal? Okay, I hope the question is clear. We will solve it in two ways. We will solve it in two ways. First thing is, we will calculate how much effective green time I have in 1 hour, because during effective green time I know the gap between the vehicles. So if I know how many seconds of green, effective green is available in 1 hour, then I will use the gap to calculate the number of vehicles. Okay, I will do it step by step, so don't worry. First of all, one cycle takes 60 seconds. So in 1 hour, how many cycles I can have? Okay, so 1 hour has 3600 seconds and one cycle is taking 60 seconds. Okay, so how many cycles I have in 1 hour? Yes, 3600 upon 60, how much? Okay, so in 1 hour I have 60 cycles. Okay, in one cycle I am getting how much effective green for this movement. Now how do we calculate effective green? We take the phase time. Phase is green plus yellow plus all red. They are representing yellow and all red both combined with capital Y. Capital Y is not yellow, capital Y is yellow and all red both. So G plus capital Y is complete phase time. Then I will subtract the lost time from it. Okay, so they have given me green time 27, yellow and all red 4 seconds, and TL is total lost time. Total lost time is this plus this. Okay, so this is also 4, 2 plus 2, just for your understanding, 2 plus 2. So plus 4 minus 4, I get 27 seconds. So in one cycle, this movement gets 27 seconds of effective green. And in 1 hour, I have 60 cycles, right? 1 hour I have 60 cycles. So one cycle has 27. So how many seconds for 60 cycles? Okay, so I calculate how many seconds in one cycle for the effective green, and I calculate how many cycles in 1 hour. I multiply them, I will get how many seconds of effective green in 1 hour. So I got 1620. Now during this time, the vehicles move at saturation headway. So there is 1620 seconds available in 1 hour for this movement, in which cars are moving with a gap of 2.4 seconds per car. Okay, so if I want the number of cars, number of vehicles, (1620 seconds total I have, and the gap between each car is 2.4. So this is how many cars I can have in 1 hour. Okay, 675 vehicles. Okay, this is method 1. Any questions? Okay, method 2. Method 2, we will use a ratio. Okay, now I have already calculated effective green time for one cycle, right? So in one cycle, 27 seconds of effective green. Okay, so I can calculate a ratio which is called the G by C ratio. Okay, G I know 27, cycle, C is cycle time, which is 60. Okay, so I got G by C ratio. Okay, So if G by C ratio is equal to 1, if G by C ratio is equal to 1, means the complete cycle is having effective green. There is no lost time in the whole cycle. Okay, then I will achieve a flow rate which is called as saturation flow rate, because in the whole cycle the vehicles will move at minimum headway. If the whole cycle becomes effective green, then the whole cycle vehicles move at saturation flow rate. Okay, so saturation flow rate, remember, inverse of saturation headway. So how much is this? Okay, so this is without any lost time, right? This is when the whole cycle is effective green, but I know the whole cycle is not effective green. Okay, I know only 0.45 of the cycle is effective green, G by C, right? Okay, G by C is 0.45. That means out of the whole time, only 0.45 is effective green. So out of the whole 1500, I have only 0.45 available. So this is another method of calculating the capacity. Okay, so you can see both methods are giving you the same answer. Do you have any questions? Is this clear? Okay. Moving on. Okay. So if you understood the concept, now you will understand this derivation very well. One phase has a lost time of TL. So TL is a combination of startup lost time, clearance lost time. You add them together, you get the full lost time of one phase. Now, one phase means for one movement. Signal has multiple movements, so we have multiple phases, and every phase has a lost time of TL. So how much lost time for the whole cycle? Number of phases into lost time of one phase. Okay, so if the signal has 3 phases and each phase has a lost time of 2 seconds, so the complete lost time will be 3 into 2. Okay, then this is what we have done in this question as well. 3600 upon cycle length. This will give you number of cycles in 1 hour. Remember the first step of the last example. Okay, this is what we did. We calculate number of cycles in 1 hour, which was 3600 into upon cycle length. Cycle length was 60, so in 1 hour we will have 60 cycles. Okay, so this bracket, the term inside the parenthesis, the ratio, gives you number of cycles in 1 hour. Okay, and every cycle I know has a lost time of L. So I multiply number of cycles of 1 hour with lost time of one cycle. I get number of I get lost time of the whole hour. Okay, I get lost time of the whole hour. If from the cycle length you subtract the lost time, you get effective green of the whole hour. Okay, what was effective green? Available time minus the lost time. So total available time of the hour minus the lost time of the hour, you get total effective green of the hour. Okay, and then if you want the capacity, again this is from method 1 of last example. During effective green, the gap between the vehicles is equal to saturation headway, which is H. So total time available divided by gap between the vehicles will give you number of vehicles, VC, which we call as the capacity. Okay, this is exactly step by step what we have done in the last example in method 1. Okay, so now if you look at the equation of VC, it has TG in it. I know TG equals to this thing, and in this thing I have LH here. LH equals to what? This equation. In this equation I have L here. L equals to what? This equation. Okay, so we substitute the values of each of the parameters from the equations which we have from these four steps. So Tg is replaced by Tg equation, LH is replaced by LH equation, L is replaced by L equation. Okay, so you replace all of them and the Vc equation becomes very complicated, which you can see here. This is after substituting the equation of all the variables. Okay, so this is coming from these four steps basically. Okay, so I explained each of them. We reach to the last step. In the last step, then we start expanding the equation, and this is what you got. Now if you look at this equation and the Vc value, Vc is the capacity, right? Vc is the capacity, the maximum volume you can have on the signal. So in this equation you have H here. H is the saturation headway. You have N, which is number of phases. You have TL, which is lost time in one phase, and we have capital C, which is the cycle length, the time of the entire cycle. Now if you look at this equation, okay, what will happen to Vc if I increase the number of phases? What will happen to Vc if N is increased? Will it increase or decrease? Yes, tell me. This is the equation you have. So if I increase N, what will happen to Vc according to this equation? Okay. What about the other 5 people? Okay, so like I did last time, okay, you can see the screen. This is what I'm doing. Okay, it will decrease. Yes, it will decrease. Most of you were correct. Okay, because you have N here, which is negative. Okay, so if I increase N, Vc will decrease. Okay, which is what you can see here as well. N is increasing, Vc is decreasing. Okay, now you look at the cycle length, see here, okay, and you see the reverse relationship here. When I increase the cycle length, Vc also increases because C is in the denominator of negative. Okay, so there are two rules which we get from here. If you increase number of phases, your capacity will decrease. Why it will decrease? Because I told you each phase has lost time. So if you have 3 phases, you have lost times 3 times. If you have 4 phases, you are repeating the lost times 4 times, and so on and so forth. And what about the cycle length? Cycle length increases, capacity increases. Cycle length means time of the signal. If you give more time to the signal, you can have more vehicles passing during the time. Okay, so this is a relationship explained, which is in this figure as well, in this graph as well. Now what is the logic behind it? I already told you mathematically how it is happening, the lost time and the total time. Now the point is, the best thing looks this one, right? This is the best scenario. Okay, the best scenario is this point. Okay, where we have 2 phases only and we have a very large cycle length. This is the best scenario, the highest capacity, VC, highest capacity. Now, is it possible to achieve this scenario? The answer is very difficult, because one phase means one movement, right? And the next phase means the next movement which is conflicting. Okay, so how many intersections you will find where there are only two conflicting movements? Maybe a three-leg intersection which has a one-way street and something. Otherwise, if you have a normal intersection, okay, this four-leg intersection, okay, so we have multiple conflicting movements. We have here and two on this side. Okay, so for these conflicting movements I need to give them more phases, right? I cannot allow two conflicting movements which can crash into each other in the same phase, so I need to increase the number of phases. Okay, so it's very difficult to have only two phases. Okay, and what if okay, the next best scenario can be, you can say this one. Okay, have more phases but increase the cycle length. Increasing cycle length will increase VC as well, as much as we can. So increase the number of phases, but at the same time have higher cycle length. Now cycle length means what? I told you, cycle length is from one red to the next red. When signal becomes green to the next time signal becomes green. So this is cycle length. So if the signal became red, okay, cycle length is the time you have to wait till the next red. Okay, or cycle length is the time, so during that time, okay, other directions are having green, right? So when you go from one red to another red, your waiting time is increasing. If your cycle length is increasing, your waiting time is increasing as well. Signal is red, okay, so cycle length is, let's say, 60 seconds. Okay, so from one cycle to the next cycle, from one green to the next green, I have to wait 60 seconds. If cycle length is 100 seconds, so from one green to the next green, I have to wait for 100 seconds. Okay, so from one green to the next green, I am waiting, right? So every time you increase the cycle length, you are increasing waiting time for the drivers as well. Okay, this is, drivers are not counting cars. They don't know that when you are waiting more, I'm also passing more cars from the intersection. What they are looking at? Their watch. Their watch says, oh, you have been standing at one place for more than a minute now. So they get restless. Yes, they get frustrated. They get stressed. They think the signal is not working properly. Okay, so then they do things, you know, the things which we all do. Okay, go into this lane, that lane, signal is yellow, signal is about to become red, I don't care. Okay, I will go and bang into the car in front of me if I have to. If I have to push the car in front of me and let it pass the intersection, I will do it. Okay, because I know that if the signal becomes green, I don't pass, I have to wait for two more minutes. Okay, so this is where the trade-off comes. This is where you have to compromise. Okay, so the best option is not possible every time. This was the whole idea behind this. Okay, now now you see here, if I put a specific value of C, I can know how much volume I can pass. Okay, but what if I'm designing the signal? If I'm designing the signal, the situation will reverse. I'm trying to design the signal, that means I don't have C. Okay, but I'm designing for a demand, so I have VC. Okay, so then the situation reverse. I need to reverse the equation. So this is the equation reversed. Okay, not this one, sorry, this one. So this was the actual equation. Now I reverse this equation to find out of our design. Okay, so this gives me minimum cycle length to pass this much demand. Okay, so the same equation is reversed. Now there are two things. So this is now volume. If you remember the previous topics, in the previous topics, capacity was always flow rate. Capacity was always flow rate. I have volume here. I need to convert it to flow rate. So I need to incorporate peak hour factor here. To convert volume to flow rate, I will divide by peak hour factor. So the capacity will be in terms of flow rate. So signal will become safe even for 15 minutes intervals. Then another thing is, in the peak hour, I don't want my design volume to be exactly equal to the real demand of the road, to real flow rate of the road. Okay, I need some cushion, I need some factor of safety. So that's a factor of safety is termed as V by C ratio. Okay, so I insert a V by C ratio to have a factor of safety of around 10-20%. Okay, so you can see in the equation both these factors are inserted here. Peak hour factor is converting volume to flow rate. Okay, so that I don't go beyond capacity even for 15 minutes interval. And V by C ratio is my factor of safety. So if V by C ratio is, let's say, 0.8, that means my capacity is more 20% more than my actual demand flow rate. Okay, so this is my factor. So this is the final equation for design. Okay, so this is from where we started. Then we reverse the equation. But in terms of there was no factor of safety and there was no flow rate. So I added it and I got this one. Okay. Yeah, so we'll do the examples next time. Any questions here?